Morning is Katrine Woody, and she's going to be talking to us this morning about her work on production of green parts using beam shaping for green powder bed fusion of metals. So I'm just going to bring Katrine to the stage. There we go. Welcome to the stage, Katrine. So Katrine, or Professor Woody, studied plastics and rubber engineering at the University of Applied Science. I might pronounce this horribly, I apologize. Würzburg-Schweinfurt. Finished her PhD at the Friedrich Alexander Universität Erlangen-Nuremberg in the field of powder and beam-based additive manufacturing in 2017, so five or 6 years ago now. And then in 2019, she was appointed as assistant professor for laser-based additive manufacturing at the Technical University of Munich. So all that remains for me is to say thank you to Katrine for coming and speaking with us today. I will disappear until about 20 minutes into your presentation, and then hopefully we'll have time for some questions then.
Okay. So thank you very much for the kind introduction, and actually you pronounce almost everything right. So and welcome also from my side. I think all of you should see my screen now. So the talk of today is about a new EU-funded project, which we get here at the Technical University of Munich last year. The acronym of the project is InShape, and the presentation today is about a concept of green powder bed fusion of metal through beam shaping. So what the idea behind the project and behind this investigation is to increase the sustainability of laser-based powder bed fusion of metal processor through beam shaping. So first of all, a kind introduction. So I'm professor in Munich at the Technical University of Munich for laser-based additive manufacturing, and the project with the title Green Additive Manufacturing through Innovative Beam Shaping and Process Monitoring started at the mid of last year. And the duration of the project is for 3 years, and the budget is around 7 million euros. And I mentioned it before, it's funded by the European Commission. And the aim of this talk is to give you on a glance an idea on the methodology of the project, what we would like to achieve, and what the motivation behind the project was. So I think all of you are familiar with laser-based powder bed fusion of metals, the process itself. And I think a lot of you know different application fields. And this is one application field, for example, these hairpin structures, so the copper structures here, are processed, for example, by additive drives via laser-based powder bed fusion of metals. So this technology is well established in industry. It's one of the additive manufacturing technologies with a really high maturity level, but nevertheless, there is a high potential for innovation in this process. And this potential for innovation is visualized on this graph. What you can see on the left-hand side is study from Roland Berger, and this study compared different components which were produced with mass production technologies, which are these gray ones here, and additive manufacturing technologies, and they calculated conventional processes, the material cost, for example, and the process cost, and compared it with additive manufacturing processing, the post-processing cost, and the material cost. And what you can see quite nicely, especially for mass production, for common rail or specific brakes or sun gears or impeller structures, in many cases, the mass production conventional process, which means casting, for example, or milling, is a very much cheaper than the additive manufacturing production route. One example, in this case, it's a little bit different in the case of a turbine blade, but there we are in the area of small series production. So our motivation behind the project is that laser-based powder bed fusion of metals is at the moment too rich and for some applications not economical, which means the aim for us is, first of all, to increase the production speed of the processes, but in parallel also to decrease the costs per part, for example. So from our point of view, laser-based powder bed fusion has a great potential to contribute to a more sustainable future. And that's why with this still young additive manufacturing technology, there is further optimization potential. And this EU-funded project with the acronym InShape is aiming for an increase in productivity around 7 times, a decrease of part costs dependent on the different parts, and we have different use case partners all over Europe, and I will show the partners from this project later. And we would like also to reduce the energy consumption to come in the direction of a more sustainable manufacturing technology and scrap material. Like in laser-based powder bed fusion, you have scrap material when a building process failed, but also scrap material in form of powder, which cannot be reused for powder bed fusion later on. So these are the, let's say, KPIs we are aiming for. It's quite ambitious, reduction of costs around 50%. And if we think back on the slide before, then for some applications, we are in an area where additive manufacturing or a laser-based powder bed fusion is really attractive. So what is the methodology in the project? So actually what we are changing here, you see a video and a zoom now on the light engine. Actually, the thing we are changing during the process is the optical module or the light engine. If we dive a little bit deeper into, first of all, a conventional established process in laser-based powder bed fusion, what you can see is a highly dynamic process. So the white area is the laser material interaction. So you see this highly dynamic process with the laser material interaction. And what you can also see is a lot of spatter formation. So these spatter, you saw the spatter flying around. It's a highly dynamic process. And due to this highly dynamic process, the spatter formation, overheating effects, there is quite a high probability that you have defects in your component. And actually, our aim is, first of all, to increase the production speed, but also to decrease, let's say, or to increase the stability of the process. So the state of the art is that if you're using typical Gaussian beam profiles, which is again the video on the left-hand side, you have these really high energy input on one single point, which means you have really high thermal gradients. And these high thermal gradients on a really small scale may lead to overheating effects, to spatter formation, so the mechanism we've seen before, or to keyhole formation. And the challenge if you have keyhole formation instead of, let's say, the transition between conduction welding and keyhole welding is that you have a quite high probability to have keyhole porosity. And this is at the end, again, a defect in our final component. So what is the methodology on a glance behind the project? What we are aiming for in the methodology is that we will develop an AI-based beam shaping unit, which means we have a novel optical model where we have a programmable beam shape. What does this mean? I have some pictures on different beam shapes later, but it means that we are able to change the energy input from this point-wise typical Gaussian energy distribution to any energy distribution you can imagine. So what we are doing is that we are changing the energy input in size. Actually, we can also change it in time, but here we are mainly changing, let's say, the picture we project on the powder bed. And the idea is that we tailor this beam shape based on melt pool characteristics, but also based on the material and based on the geometry, for example. If you have, for example, really filigree structures, the idea can also be to separate the beam in or split the beam in 3 different beams to increase the production speed. And the output is then an AI-based recipe book for beam shapes, for material properties, or for a specific feature of your final components, let's say filigree structures or specific overhang angles. So if you change the energy input, it's really important that you understand the temperature development during processing. And that's why the project is underpinned not only by this one innovation, but by another innovation, which is that we would like to implement so-called multispectral monitoring or inline monitoring and control into the powder bed fusion process. What is multispectral imaging? Multispectral imaging is typically used not in the wavelength area of the IR, in the IR area, but in the visible light to separate, for example, different areas, different areas from each other. So we try to use this technology to get an idea on absolute temperatures during laser exposure. And this is for us helpful to understand better, let's say, the influence of the different beam shapes on the thermal household. But today I will mainly focus on the topic of beam shaping and some first results. So the innovation here is that we are able to shape our beam, our energy input in space. And on the left-hand side in this picture, you see the typical Gaussian energy distribution, which means a really high energy in the middle, and in the outer area, the energy is decreasing. So this is a top view. If you would have a side view, you would have this typical Gaussian shape. And what we are able to do with our novel optical engine or optical module is that we are able to change the size of the spot, but also the shape, so the picture we are projecting on the powder bed surface. Here you see one picture, which could be a donut profile, for example, or a top hat profile, but there is also the possibility to create these C-shape profiles or line profiles. Actually, you can create any profile you can imagine. But the question is always, what is the perfect profile for this kind of material and for this type of feature? So by increasing and changing this energy input, the aim is to decrease the dynamic of the process or to increase the productivity. And what you can see in this video is actually a first video with one beam shape. The beam shape we used here is the C beam shape you've seen before. Oh, I could go back to the video. And what you can see quite nicely is that we have a really smooth melt pool. We have less spatter formation. It's, of course, a slow motion of the process here. The production speed in this case, so the scan speed was not higher, but maybe you see it, the exposed area is bigger than a typical Gaussian beam profile. Typical Gaussian beam profile has a spot size around 80 microns, and we have here a spot size which was bigger. But what you can see is you have here the powder bed. You cannot see actually a denudation zone, and you have a really, really smooth, less dynamic melt pool, and also the number of spatters you're creating here is way much smaller. So these are the first results. What is ongoing investigations is, of course, to analyze the influence on the different beam shapes, on the resulting microstructure, also on resulting properties. And we are also changing the beam shapes you've seen before. So there's one paper, for example, available where we calculated a specific beam shape with the idea to get a very homogeneous temperature distribution, and then the beam shape looks a little bit different than these C-shape beam shape we have seen before. So to sum it up here a little bit, what the idea is. So the idea is that we have these AI-based process design and control. Therefore, we are using a novel kind of light engine, which was developed from EOS. And now we further develop and implement these tools for different types of materials. In our case, we are mainly focusing at the moment on Inconel material and try to understand the influence of the different size of the beam shape and the different beam shapes on the process behavior and later on the component properties. And in the future, this is combined with this multispectral process monitoring setup. And the idea is then really to control the process based on the melt pool characteristics, the features, and the materials we have at the end. So actually, the idea is also to transfer this technology in the future into industry. And therefore, we have in the project 4 different use case partners. The use case partners are in different application field. One use case partner, Aenium, which is located in Spain, is in the area of space. And they try to manufacture components of a combustion chamber with a specific copper alloy. And the aim in this use case, for this use case, is to increase the productivity and to lower the surface roughness, to have a better flow behavior, and additionally to control the microstructure, because for coupler applications, the control of the microstructure is always important to get a higher conductivity, for example. Another use case in the area of space or aviation is from Oerlikon AM, which is an impeller structure. The material here is an Inconel material, and the aim is mainly to increase the productivity during processing or of the process, to lower again the surface roughness on specific surfaces, to avoid support structures completely, and that's why to also lower the overhang buildability. And here you see a cross-section of this component. Further use cases are in the area of consumer goods on the left-hand side, or in the area of energy. A use case partner, Amexi, which is located in Sweden. There, the use case is a cylinder head for a chainsaw, which is another type of material. So also, let's say, the material variety in the project is quite huge. It's an aluminum alloy, and they are mainly aiming for increase of productivity. And for this use case, for example, the let's say, density requirements are not that high compared to the combustion chamber in space or to the impeller we've seen before. And another part from an industrial gas turbine is brought by BMED, which is located in Italy, again, an Inconel material. And actually, the main goals are quite similar. And if you compare the different application fields and different use cases, everyone at the moment is actually aiming for an increase of productivity, a lower surface roughness, and somehow the to decrease the overhang buildability or to tailor the microstructure. Here you see the team of the InShape project on a glance. So I'm professor at the Technical University of Munich. We are closely working together because EOS is also close by here with EOS, who has developed this beam shaping unit, and with Oerlikon, who is one of the use case partner. Then we have the Bavarian Research Alliance, the Technical University of Eindhoven is contributing in the area of artificial intelligence. Technion is dealing with the topic of multispectral imaging, and then we have the 2 use case partners, or the 3 use case partners, Aenium, Amexi, and BMED. And Celius from France is a partner who is dealing with multispectral imaging and supporting us in delivering a multispectral setup. So to sum it up, this is our idea to use beam shaping in the future to bring laser-based powder bed fusion to a more sustainable process for a more sustainable world in the future. So thank you very much for your attention, and feel free to ask questions now.
Thank you very much, Katrine. I was certainly fascinated by that. You had some amazing videos in there, which was wonderful. We have a couple of questions. So first question and then the Q&A, and thanks to our participants for sharing questions. First one, so the question is the research conducted for metal or polymer processes? I guess I might extend that question to, do you see it being applicable across different process types?
So actually the project is mainly dealing with metals. So not mainly, it's only dealing with metals. You've seen it before. It's for an nickel-based alloy and for aluminium. And so we are applying our research on this topic for these materials. You can extend it to all metals. I think it can even be extended to metals which are, let's say, in the category and not easy to weld, so difficult to weld materials. And actually, I'm planning a project on the topic also to transfer our insights in this process to plastics, because my chair is actually dealing with metals and plastics, but then the beam shape would look a little bit different. Here, our aim is to decrease the process dynamics. In polymers, the polymers are more the lazy guys on the party, so therefore these dynamics is not important topic. But actually there are, let's say from our point of view, you can transfer these results maybe to other materials.
Wonderful. We did have another question asking about whether some materials work better than others. Excuse me. I think you've probably covered that. We have a quite technical question. What kind of challenges do you see when using the beam shaping light engine?
The challenge, of course, and one of the hugest challenge is that the tool is that powerful, you can actually create every picture you would like to create. So the question is, what is the target value, first of all? Is this really only productivity, or is it to get a specific thermal household, to get a specific microstructure, because the tool can, from my point of view, do that? So that's the challenging part, that we are increasing the degrees of freedom dramatically. That's the challenging part. And one question is also how, let's say, large or huge can a stable melt pool really get? And this is something we are addressing.
Wonderful. We've got one last question, which I'll take just very quickly, though. Are you around for any of the networking sessions at all?
Yeah, I will be here, let's say, the complete morning.
Okay, so I think for anyone, if you do have questions or you just want to chat more about Katrine's work, catch her at one of the networking tables in the later session. But last question for you there. What productivity is achieved now, for example, for ALSI 10mg? As a non-metals person, that's a handful for me to say. But yeah, I guess because I think you mentioned I wrote down 7 times productivity. Like, how close to that are you?
Yeah, so actually the project has just started. So we are doing our first investigations. What we know is, and what we have already done is that it's what you can easily change is, so the typical spot size of a Gaussian beam profile is around 80, 90, maybe 100 microns. And what we have done in the past is that we can increase the spot size around 500 microns, which directly increases the productivity. Because then you have less hatches and so on. But I don't have any number yet. So that's the final, let's say, goal we would like to achieve.
So I'm very hopeful that you'll be coming up and speaking again at the end of the project and telling us all about the things you've done. We'll say you were there at the start. So thank you very much. Obviously, we'd be having a big round of applause now if we were in an in-person conference. That was wonderful. I'm going to send you off the stage. I can see claps floating in on the chat channel. So if you can't see that, they are coming in. Thank you very much. I'll send you back to the floor.